Okay, hi everybody.
Morning, Professor.
Morning.
Let's see, let me just get all my windows properly configured on my screens. Okay, oh, and let me just grab my pen. Okay, so I see there's some people in the chat. Let's take a look what that is. Oh, good morning, yes. Hope everyone had a good weekend. So we have essentially 4 more classes, lectures, and then on the finals on Tuesday in person. And Monday, I'm just going to do a review day. I just think we'll all be wanting to have time to do a review day on Monday. So there's only 4 days left. 2 more days of Greek math, and then 2 days to get us from 200 BC up until the 1800s. So that will be interesting 2 days, but I'll pick and choose. Obviously, only be able to pick a few things from those that over 2,000 year period. But you have to give Greek math its due time because they advance things so much. And today there are 3 things I want to show you. Strange, hold on. Okay. Hold on a second. Let me just get my pen charged up. Okay. Ooh, I don't like that. Okay, give me a second now to fix up my iPad. Okay, let's try this again. 865214619.
Professor, one of the assignments, it says, is history of math, and it just gives a whole list of theorems, and it says due today. Greek geometry, class number 9, due today. That's not an assignment, is it? That's just a...
No, that was just a list. Let me take a look at what you're talking about. This.
Yeah, I just got a
The assignment was just to do the four constructions.
Okay, that I did. Okay.
This is a collection of the different constructions that we did.
Right. Okay.
Okay. So the culmination of now Euclid's Elements has 13. They call them books. They're more like chapters. And book 1 culminates with proposition 147 and 148, which we think of now as the Pythagorean Theorem. Now, most proofs of the Pythagorean Theorem, we see those like the Chinese one where It's kind of like a dissection proof. There's like a diagram, and we're showing that the two smaller squares, have the same area combined as the large square. There's also one proof that I mentioned. No, the project's not due today. It's due next Monday. And I'm going to post a second. I just looked through the old projects and saw one that got 100 and thought, oh, everyone wants to see which project got 100. But you don't need all that detail to get 100. I'm going to look through to find someone who got 100 who had much less detail with the Common Core standards and such. For the math teachers, I'm really just looking for, what would your plan be? That I see that as a 1-page thing, and then 2 lesson plans that are like 2 pages each. This is not meant to be, when you're an actual teacher, you have to plan up to 3 lessons every single day. So oh, it says today on the Google Classroom. Yeah, I better change that. When you're actual working teacher, you do 3 lessons a day, perhaps. So doing 2 lessons over a period of a couple of weeks, plus an outline of how those 2 lessons fit within a larger unit is reasonable. And also, I'm going to grade these very generously. It's the final. That's the big thing. You have to be learning. You have to be learning the math.
Yeah, I appreciate it for the non-math teachers who are learning to be math teachers. It would be helpful for any sort of guidance.
Yeah, I'm going to post a different, your lesson plan could be informal. Just imagine I just said you have to go talk to a bunch of people about this. It doesn't have to be that great, that thing. I like to have those things, so if somebody bombs the final, at least they got like a 90 or 100 on the pretty easy project. The project's not the thing that's going to bring down your grade. Over the years, I've seen people get 20s on the final sometimes, and most people don't. Most people do very well on it, but I've seen it. So I want to give you a little bit of padding by having a project, but for sure you want to be learning the math, because that final is a math test.
Yeah, that's been
now
Yep.
The math. Yeah, if you focus on the math, you're in pretty good shape. I'm moving this to tomorrow. Yeah. So the Pythagorean Theorem proof is based on a pretty famous diagram from Euclid's Elements. And here's what the diagram looks like. This diagram is sometimes called the windmill, because it kind of resembles a windmill with all those lines. And sometimes it's called the bride's chair. Presumably, it looks a little bit like, I don't know where the bride comes in, but presumably it looks a little bit like a chair, I guess. But it's called a windmill. And this is a very, very famous diagram. As you can see, it has a right triangle over here. That's your right angle. So it's a right triangle with the hypotenuse is the base. And then on the sides of the triangle, we have 3 squares. These are our small and medium squares, the a squared and the b squared. And then on the bottom here, we have that large square, which is c squared. And the goal of the proof is to prove that the blue and the green together have the same area as the purple. And they want to do it with Euclidean geometry, meaning like theorems and statements and reasons, and not like the geometrical ones that I've shown you before were kind of informal. This is going to be like a formal proof. And I'm going to just give you the big picture first. There's also 5 extra lines drawn in that are a little bit mysterious. There's there's a line here. That's the altitude drawn from the right angle to the hypotenuse. So this is a right angle, and it actually continues all the way down. Then there's these four other kind of cryptic lines. 1, 2, 3, 4. And somehow, with all these lines, those lines form a bunch of triangles now. And book 1 is all about triangles, pretty much. So some of these triangles that got formed by those new diagonal lines are going to be important.
So, Professor, you're going to explain these 4 supplemental lines, right? Because I can't quite even find them with all the ink there.
Well, yes. Well, one line went, these 4 supplemental lines, one line went from this corner of this square right here.
Yeah.
All the way to the corner of that square there.
Okay, thank you.
One went from this corner up to that corner. So
Okay.
one went from this corner
Yep.
down to that corner. So we're always joining corners of squares,
And
and
then,
one went
yeah.
from this corner to that one. So that's where that's how the 4 lines are drawn.
Thank you for doing that. I can see it now.
We'll see these a little bit better coming up also. Now the plan is to show that this small square has the same area as this rectangle here. So you see that altitude, the first line that I drew, it splits the big square into 2 rectangles. And the plan is to show that the little square has the same area as the left-hand portion, whereas the square here has the same area as the right rectangle on the right-hand side. And if you can do that, well, then a squared plus b squared will equal c squared, because a squared will equal the orange part, and b squared will be the purple part, and together they will combine to make the big square on the bottom. So that's like the overall plan. I actually have in here, I have a lot of links in today's lesson. One of them, this is real intimidating when you look at this, but I'll show it to you still. This is the actual translation of the proof in Euclid's Elements. See how they describe it? In right-angled triangles, the square on the side subtending the right angle, which means the hypotenuse squared, is equal to the squares, sorry, the square on the side subtending the right angle across from it is equal to the squares on the sides containing the right angle, namely the 2 legs. And here you see the windmill diagram. And you can see that it's a lot of lines long. Spends a while proving that square, in these days when they would describe a square, they would, squares and rectangles, they would describe with 2 letters a lot of the time. Let's see what they do here. Therefore, the whole, wait. See, they say square GB. They're just talking about what we would call ABFG, but they define, when they describe quadrilaterals, they just have to say the names of 2 vertices that are diagonal from each other. So they can say square GB, and that's what we would call square ABFG. And likewise, this this rectangle BDL. They don't even say the point in the top right corner of this rectangle, but they'll call that rectangle BL, I would bet. Let's see. Yeah, they call it parallelogram BL. It's a rectangle. They spend all their time proving that the square ABFG is the same area as the rectangle BDL, whatever at this point would be called. And then they don't even do the other part. Then they say at the end, likewise, using a similar argument, this square is equal to this. So they actually, if you wrote this up formally, it would be twice as long, because at the end, they say similarly, these last two lines, 3 or 4 lines, are basically saying you could do the same thing on the right-hand side also. So let's dive into what we need to know to be able to follow this very famous proof. Again, let's keep the, oh, and I need to charge this pen, so hold on, let me move this. Oh, there we go. Okay. Again, keep in mind the plan. The plan is to prove that each square is equal to a piece of the bigger square, and therefore the two squares together will equal the full square.
So, Professor, can I ask a question? Are we going through this to actually learn to construct it, or are we just trying to take away concepts? Because, you know, it is getting close to the final. I just kind of want to keep an eye on that. So how is it best to process?
Oh, well, so this isn't a construction. So some of the propositions in Euclid's elements are constructions, and some are like what we would think of as like theorems. So he's giving us the diagram. It's already made.
Okay.
And we're trying to use that diagram to prove a theorem. So a construction is like, okay, I'm giving you a angle, and what steps would you use to create the angle bisector? But a theorem is more like prove that it's always true that vertical angles have to equal each other, or prove that it's true that the isosceles base angles of an isosceles triangle. We haven't done, the only thing we've done so far is constructions. I suppose we did a proof. We did the proof that the Thales theorem, that was a proof.
Okay.
But it's not really, the Thales theorem is like a proving that some, rule is always true.
Okay.
So this isn't a construction. This is a proof of a theorem.
Okay, cool. Thank you.
We don't have to create the diagram. It's already made for us.
Okay, great. Thank you.
Yeah, so like about a third of the propositions in Euclid's elements are constructions. The other 2/3 are theorems, and those theorems generally support the constructions that are happening. This one's a theorem. Here's our diagram. And there is, I'm going to bring up something over here. No, I'm going to bring up something over here. There are a couple of theorems you have to be aware of. Oh, of course. I think in assignment 9, I posted a link that I want to use here. No, History of Math 2022. I'm going to post another link with more of these sorts of sketches that will help us understand. Let me come back over here and grab. I'm going to post this link right now for you so you can follow along with it. Books. That's probably here. Greek geometry for. Yes. Let me share this with you. Here you go. I'm gonna throw it into the chat, but I'll also put it into the Google Classroom. And chat to is everyone. And don't worry, this is also going into here. Okay, this has a lot of good construction or good diagrams here. First of all, here is something that Euclid proves that I'm not going to make a big deal of. I'm just going to kind of look at it for a minute. We don't have to know the numbers of this or anything like that. But since Euclid's Elements, the goal of book 1 is to get to proposition 47, which is the Pythagorean Theorem, most of it builds to that. Check out this picture. Look at this. Here I have a parallelogram whose area is 6.65. And here's another parallelogram. And notice how it has AB, this bottom line. It's the base of both parallelograms. But look at how the two parallelograms have the same area. Oh, someone asked, if the link is in your name, we cannot save or turn in. So in the when I assigned the 4 constructions for homework, those were done like a special way through the Google Classroom. And those you could just, whatever you do, get saved and I get to see it. But these general ones aren't things that, you could change your own, you could change it, but I won't see what you did on it, these other ones. So I just made a special way for the homework so you were able to like do it and I could see for each person what their stuff was. So these are meant to just be played with and not to be like you have to turn these in or anything. Check that out. Anyone want to say, why is it that these two parallelograms have the same area? You want to volunteer for that?
They have the
Yeah.
same base.
Yes. Literally, they have the same base. Is that enough though?
And they have this,
parallelogram that has that.
they also have the same height, which isn't that the formula of area of a parallelogram?
That's exactly right.
Yeah.
They have the same height also. Now, part of that has to do with these parallel lines. I should have mentioned this. This line CE is made to be parallel to AB. So I should have mentioned that. If that line wasn't an extension, well, of course it's a parallelogram. If the first thing is a parallelogram, that's a parallel line. And that causes both of these parallelograms to have the same base and the same height. So that's kind of cool because they don't look like they have the same area. But if you believe the formula for area of a parallelogram is base times height, then you'd agree that these parallelograms have the same area. Why don't I put that in over here? Some like prerequisites. 136 says that two parallelograms that have the same base and the same height. Of course, the height is, if I make the full parallel lines, the height of a parallelogram is the height, sort of the perpendicular distance between the two bases. It's not one of the sides. And this other one has its height here. So yes, area of parallelogram is base times height. And since the two things have this literally the same base, I mean, their heights are equivalent, but their bases are literally the exact same line segment.
And
That's
is that
136.
definition 36 or proposition 36?
That's proposition. They do a little proof that they have the same area, but we're just gonna just think of it as, okay, they're both base times height. They have the same base and height, therefore they have the same area.
Okay.
He does like a somewhat involved proof of it. But for our purposes, we look at it as, okay, base is the same, definitely, same exact line segment, and the height is the same because of the way those parallel lines are. Now, then proposition 41 is very similar. But in this one, I have a parallelogram, and then I extend the top base, and I put a point randomly on that top base, and I create a triangle. And you'll notice that that triangle area is half the area of the parallelogram. I can change my initial parallelogram. I can change this point here.
So does that mean a parallelogram can be divided into two congruent triangles?
Oh, for sure. Now, they may not be congruent to this third triangle, but yes, you can take any parallelogram. In fact, that's where your proof of that a parallelogram in general, or that the area of a triangle is 1/2 base times height, because any triangle can be sort of reflected sort of over itself to get a second triangle. And if the parallelogram was base times height, then the triangle is 1/2 base times height. And likewise, if you started with a parallelogram, the diagonal will definitely split it up into two congruent triangles, side, side.
Which is proposition 8, right?
Yeah, 8 was side, that's right. So 41 basically says that the area of a triangle is 1/2 base times height. But more specifically, they say if you ever have a parallelogram, and then you have another point here, which is on that top base, and you join these three things, that triangle's area will be half the parallelogram's area. Or said another way, the parallelogram is equal to 2 times the area of the triangle.
Yeah.
So if we ever see something like this, a picture that has some kind of parallelogram and some kind of triangle, we'll be able to say that that rectangle in this case is double the area of that triangle. So keep that in mind, because this thing is going to appear 4 times in the Pythagorean theorem proof. But it's hard to see with all those different lines. Okay, so that's all. That's the main theorem we need. That yeah, and theorems we already have. So let's dive in. Oh, now here is a picture, and I actually put, let me bring up in the Desmos activity. I have a question for you. So let me bring up Desmos. Where is my? I'll give you the code. The code is actually in the Google Classroom. You know, there's a link for this, but I like to give you the code also, just to have the, in case your link's not working. Let me just bring this up for you. Things going a little slow on my end. Do we have the code over here? Let's just see. If you go to class number 10 and you click, wait, is it there? It's not here? That's very frustrating to me. The other one's not coming up either. Come on. Give me a second, I will get this going. Very odd. Okay, I'm not going to bring that up right now. I'm going to just go through it this way. Now here is a picture with some triangles. There's a lot of triangles in this picture, but ultimately there are two triangles that are the most important ones. They are both obtuse triangles, FBC, and I'll make this one another color, and ABD. Those triangles are, they're kind of hard to see because of the way that they're overlapping in that way, but the overlapping part is real important. Oh, I see why I didn't have, okay, so hold on, I am getting closer to letting you, because I have a nice nice picture of this for you to because it's hard to draw this picture because unless you know exactly how it's made, it's hard to draw it. Here we go. Good news. I'm making progress here. 48P RME. I'm going to put that into the chat. Okay, 48 PRME, 48 prime, no I, 48 PRME. Okay, now you have your own picture which you could draw on. Now look at the given information here. They're saying that BF and BA are both length 3, and that BD and BC are both length 5, and that BF is perpendicular to BA and BC is perpendicular to BD. So you could mark that up onto your picture. I'm going to put it onto my picture over here. So we have 3, 3, 5, 5. And we have some right angles, namely one here and one there.
So the 3 and the 5 are the legs? Or
well, 3 is a leg of the green triangle, namely this leg,
okay.
and 3 is a leg of the blue triangle.
Okay.
So yes, 3 and 5 are both sides of the green. The green triangle has a 3 and a 5 here around that obtuse angle.
Yep.
And the blue triangle also has a 3 and a 5. And those two, the 3 and the 5 sides, form an obtuse angle.
But the 5 applies to the BC and the BD, right? Just to be clear.
That's right. That's right. The 5 is the BC in the green triangle, and it's the BD in the upright. So there's like a vertical triangle and a horizontal triangle.
Okay.
So the 5, it's hard, right? Because that 5 could be representing a lot of things. So there's 2 5s in there. So it is pretty confusing because that 5 also looks like, if I were to label the AD side, that 5 would be in pretty much that same spot.
Right.
We don't know how long the hypotenuse, the AD or FC, we don't know the lengths of those.
Okay.
Now the big question is, can you prove that triangle FBC is congruent to triangle ABD? Is there enough information? All we have are those. All we know is two sides, it seems. Anyone want to volunteer and say what you could type? You certainly could type it into your into the Desmos activity. Let me just give everyone a minute, see if anyone types it in to Desmos. Let me glance at the dashboard here.
I'd also like to point out you actually have 4 right angles.
Oh, so what other angle? Give me the 3 letters for what other angle you want to call a right angle.
Well, if you're looking at the other 2, so like you've intersected a bunch of lines there, and you've got like a little trapezoid in the middle.
Oh, I see.
If you're looking at the 4 triangles, though, you have 4 right angle triangles.
I see what you're saying. You suspect that AD is perpendicular to FC.
Is it?
Well,
Because they'd have to be
there's
parallel
nothing
lines.
that
Those
says
don't
it
look
must be.
parallel to me.
It certainly looks, it definitely looks like it, but is it really? We can't say for sure.
Yeah, okay.
Now this picture of these 2 triangles actually comes in a context that has a lot more lines, and maybe AD is actually also perpendicular to FC, and that might be useful to us for some other things. But for now, let's assume that we do. Well, there's definitely not enough information to tell us that yet. Maybe it could be proved. Let me take a look at what people are saying about this. Okay, I see Molly and Beth and Vanessa. Okay, so 3 people so far have identified. So everyone take another minute on this. Can you prove that those 2 triangles are congruent? And Marcus put it into the chat. So the spoiler alert, but yes, I see those people who wrote stuff in wrote SAS. And that's correct. SAS, book 1, proposition 4. I actually personally don't memorize all the propositions, but since these ones are like fresh in my mind, book 1, proposition 4 is SAS. Where's the angle? Someone want to volunteer who's going to describe? I saw Molly and Beth had nice explanations. Does anyone else want to volunteer to explain where is the A coming from? Where is the angle coming from?
Is it the combination of 2 angles where the 2 right angles co-share ABC? So by
Yes,
adding them, they are adding the shared part, they would be congruent to each other?
that's exactly right. So this obtuse angle is the right angle plus whatever ABC is. And the other obtuse angle, this one, is also a right angle plus whatever ABC is. So angle FBC is congruent to angle ABD. Yeah, they are both 90 degrees plus whatever the measure of ABC is. And that's why these 2 triangles are actually fully congruent, because that's the missing piece I needed for SAS, book 1, proposition 4. You don't need to know book 1, proposition 4. Anytime I'm studying a culture, I really like to get my head into their way of thinking. So I sort of memorize them as I'm doing it. But then when I do a new culture, I forget a lot of these things. I won't ask on the final which proposition is SAS. So those two triangles are actually congruent. And if you taught geometry ever, this is not most likely a configuration of triangles that you ever saw. I mean, there are triangles that have shared angles and things like that, but just like this one in particular, you've probably never seen this thing, but it's actually part of, now that we have everything we need now. And today, by the way, we're doing 3 things today. Pythagorean Theorem, 147. That takes a little less than an hour. Construct regular pentagon. That takes a little less than an hour. And then Archimedes calculation of pi. That takes a little less than an hour. So that's where the 3 hours go today. So even though I fumbled a bit in the beginning with my technology and all, we're in perfectly good shape. I am in no rush, really. Okay, now you say, well, that's a pretty cool thing of 2 triangles. But check this out. In this picture here, here are those 2 triangles. Here's ABD, same letters.
Yes. And
And here it
FBC.
is.
Yes.
And here's FBC.
Yeah.
Now, if the picture was given like this, you wouldn't need to be told all that given information. You would just need to be told that BG is a square. BG, I'll call it ABGF is a square. And that BCED now, you wouldn't need to know that this is 3 and this is 4 or whatever it is, because as soon as you know ABGF is a square, you can say that this side, BF, is congruent to this side because they're part of the same square, even though one's part of the blue obtuse triangle and one's part of the green obtuse triangle. AB and BF are part of that small square. We don't know the size of it, just that they're equal to each other. Likewise, because BCED is a square, side BC
And BD.
is congruent to BD. Again, we wouldn't know how big they were, and it wouldn't matter. I gave you they were 3 and 5 just to give us something concrete to like relate to. But even if we don't know the lengths of them, just knowing that ABGF is a square, and as Scott said, we can prove these triangles congruent for the same reason. The obtuse angle, the obtuse angle is the right angle. Again, that right angle is given by telling us that ABGF is a square. So I had to tell, in the Desmos, I told you they're perpendicular, but just using the word square gives us all that given is all done by saying those 2 things are squares, and the triangles are congruent by SAS. Triangle FBC is congruent to triangle ABD. When you name the triangles, the letters, you try to make the corresponding things. It's not just, so when I called the first one FBD, I had to call the other one ABD then. Sorry. When I called the first triangle FBC, it was accurate. Oops, I don't like doing that. I think I just want. That's pretty cool. Move that away. So those two triangles are congruent by SAS. You know, that gave me an idea. Now, check this out. Remember triangle FBC, the blue one? Let me outline that. And let me make an outline of square AGFB or BAGF. And now, mind blown.
Very cool.
Yeah. The area of the triangle is 1/2 of the area of the square. Yes.
That's right. By 141, the square is double the area of triangle FBC. So now we know something about this square. Now,
So that triangle has an area of 4.5, right? Because the area of the square.
no, we don't. We at this point we don't know any of the. So
Oh.
we don't know the lengths at this point. It's all kind of all like generic.
Oh, okay.
So, but you're right. No. But did you say 4.5?
Yeah, because the square was 3 by.
You were right. If in my original picture I told you that AB was 3,
Right.
then the triangle would be 4.5. That's right.
Okay.
But in this situation, we wouldn't know the area of the triangle or the area of the square, but we would just know that the square has double the area of the triangle, whatever it happens to be.
Gotcha.
Now, to have your mind blown, remember that green triangle. And on the same picture, I'm going to outline this rectangle. Okay, does that make anybody want to make an observation now or some sort of conclusion?
The rectangle is twice the area of the triangle.
That's right. I'm gonna put a letter here. I'll call it J just to. So rectangle, L, J, B, D is all right. Area is 2 times the area of triangle ABD. So the first triangle, the square is double the first triangle, and the rectangle is double the other triangle.
Yeah.
This is so cool.
But those are two, but because the triangles have been proved congruent, because those two statements separately don't tell us anything. LJBD on its own is double the one triangle, that's great. And the square is double the other triangle. But because the two triangles are congruent, that means that the squares, they have the same area. So the squares double one congruent triangle and the rectangles double the other congruent triangle. And therefore the square and the rectangle must have the same area. So that's how that works. It's really ingenious.
So essentially, it's because they shared the same triangle with a relationship of 2 to 1, they themselves have to be equal.
Well, they're each double a triangle that's equal to the two triangles they're equal to are equal to each other. The two triangles they're double of were equal to each other in area.
Yeah, that's so cool.
So
Sorry,
that's
could
real
I ask
slick.
you to- Can I ask you to
Say that
go
again?
back 1 second? I'm a little bit confused on the square and the triangle. I see the shared base. I don't see the equivalent heights.
So you see, if I take so the tip of this triangle is over here,
Mhm.
and that is on, you see how AG kind of gets extended? This is one big line. So this is kind of like before when I had the base, they have the same base, and I take the other base and extend it. If I put the third vertex of the triangle anywhere on that other base,
Oh, okay.
it's
I
going to
see.
have the same
So
height.
it's
So
not
it is hard to
actually
see the height,
drawn, but-
because the height is actually, the height of the triangle is like that. Or maybe it's better to put it here. Usually we think of a height of an obtuse triangle as coming from here down. But to do that, I would have to extend this line also.
Right.
But maybe that helps for the purpose of
Yeah.
seeing
Yeah,
that
thank you.
triangle.
Appreciate it.
Sure. Now over here, sorry, Greek geometry. If I come over here, Euclid Book 1, Proposition 47. This is going to make it even more clear for you, because I can click here and show the first two triangles. And I can also go like that. So we can see the square. It's always easier to see these when the square, the base is horizontal. So the square has has double the area of this triangle. Here I actually have the measurements. Area of DAB. I don't know what that is. So you can see they have the same areas being measured, and you can mess around to see that it stays the same. On the other hand, if I rotate it this way, I can see that other triangle double the other the rectangle being double the area of the triangle.
Wow, that's so cool.
Yeah, well, this is actually one of the more famous diagrams in all of math. The Euclid Pythagorean Theorem windmill proof. Now, that only proves. Oh, I like to make it like that. Now I'm going to take these guys away. And then Euclid just says very casually, and I could do the same thing on the other side. Those other two triangles, they're kind of bigger. You can see that the triangle that's like CKJ, or this red square is double this triangle, and this red rectangle is double this triangle. But those two triangles are congruent for the same SAS reason. They each have a side from the medium side square, and they each have a side from the large square. And the angle, the obtuse angle in the middle, is right angle plus shared angle. In this case, it's a different shared angle. It's angle ACB, but it's the same idea.
Are you gonna leave it there so we can sketch it, or are you gonna have it build it up with us as you?
Why don't I, best way for me to do that is to come back over here.
Okay.
So on the other side, you have this triangle. And you have this triangle. Check it out. Now the obtuse, the obtuse angle. Oh, and while I'm at it, we'll throw in the right angles. And by the same reason as before, they each have, the obtuse angle consists of a right angle plus the shared part. So we have SAS again. And then by the same reasoning as before, I'm going to use green, and I'm going to use green for this rectangle. Even though this rectangle is double the green triangle, I'm going to make it green here. And I'm going to make this square blue because it's related to the blue triangle. And now, whoops. Now, we can see this square, this triangle, or this square, sorry, is double the triangle. And this rectangle is double this triangle. But because the two triangles are congruent by SAS, that's fun. Because the triangles are congruent by SAS, the squares double one of the triangles, and the rectangles double the other triangle, which makes that square congruent to that rectangle. And then put all together the thing I promised you. I like going back, something that seemed totally crazy, mysterious, the windmill, the auxiliary lines and all that. It was all about making four triangles, two triangles that were congruent to each other by SAS, two others that were congruent by SAS, and then the squares were double two of those triangles, whereas the rectangles that combined to create the large square were double congruent triangles. That's a good one. That picture, like I said, is famous. I'm sure that someone has a tattoo of Pythagorean theorem diagram. I haven't. Well, let's see. Does anyone? Well, let's see. It's called the Windmill. I'm a little, well, we're adults, but sometimes as a teacher, you best not to type tattoo of blah 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 because you might get some really unusual things coming up. I'm just going to type windmill. Well, there's too many other windmills going on.
But maybe put windmill math or Pythagorean. That might narrow it down. Math.
Oh, is tattoo spelled with two T's? Oh, well, I guess not. I'm just getting windmills. Sorry about that. It's also called the bride's chair, but I don't know that.
Don't know what that Google search will yield.
That might get some. I see this picture, but it's not done. So maybe people aren't getting
There it is.
tattoos.
Wait, no, it was there. Go back.
But was it a tattoo though?
Oh, it wasn't.
Oh,
Yeah, right there.
well,
On
this
the arm.
this person's making some progress towards it.
Yeah.
They don't have all their auxiliary lines,
Yeah.
but they do have something going on there. They have the it's hinted at
Yeah.
It's hinted at here. Anyway, I think next time I teach it, I'll get a tattoo of it. And then I can just say, and this thing's so important, here's my tattoo. And people will be they'll never forget the windmill diagram of the Pythagorean theorem that way. Get temporary tattoo or something. Okay, so and now when you come back over here and look at the really scary thing I showed you, I love it's written in first person. I say the square on BC is equal to the square. For let there be described, he's explaining how to draw the auxiliary lines here. And then he says, look, he says right here, since DB is equal to BC and FB to BA, the two sides are equal to the two sides. And here's where they say the angle. Remember those obtuse angles? Since angle DBC is equal to angle FBA for each is right, let angle ABC be added to each. Therefore, the whole angle is equal to the whole angle. That's the making the obtuse angles. Here, he says that the two sides in the angle, therefore the base is equal to the base and the triangle is equal. We don't see it, but it says 1,4 there, SAS. Then he says now the parallelogram is double the triangle for they have the same base, that's 141. And square GB is double triangle FBC for they have the same base, 141 again. Therefore, the parallelogram is the same area of the square. And then he finishes off by saying, similarly, if you drew these auxiliary lines, you could prove that the parallelogram, the rectangle, is equal to the square, and therefore the whole square is equal to the whole square, and I'm done. So you wouldn't be allowed to do that in geometry class nowadays. They'd make you redo the whole proof with all the steps and the SAS again. There's some story, and I can't find it, but there's some like poet, philosopher, I'm not sure which one, but they picked up Euclid's Elements and saw this diagram. And they read through this thing, and they didn't know any geometry. And they said, this is really intriguing. I must understand this. So they, oh, cool, someone has a go-goo diagram. Somebody saw this diagram and was so intrigued by it that they sort of worked their way backwards through Euclid's Elements so they could understand it. It's actually not a very hard thing. Like you could teach this to 9th grade geometry students. They don't. This proof is not the proof that's done in the geometry textbooks. They wait until they've done similar triangles and they do a proof that involves similar triangles. The Greeks knew that this could be done with similar triangles, so they do it again in book 6. They prove this theorem again, but they do not like similar triangles. I'll tell you why a little bit later. They don't trust similar triangles. Maybe I should throw that in right now, just for reference. Since we finished part 1 of today, there are 3 things to do. We've done part 1. On the final exam, in case you're wondering, I have actually asked this question on a final exam, just to give you an idea of like, something like that. Actually, a more fun question. I could do variations on it. I like this one even better. Hold on a second. Implied this is a square and this is a square. Sorry, you need to have these. Hold on. There you go. There's a fun. This is what I do on the final exam.
You
I
need to
ask a
get rid of that
question
4.
that if you, what's that?
Get rid of the 4.
Oh, thank you. This is my style for a final exam. I give a question that only somebody who really knows the theorem, if you know the theorem, you can answer this question in a matter of seconds. But if you don't know the theorem, you know, or the whole, this is testing, do you understand the proof of the windmill proof? Someone raise a hand and I'll have them just say their answer and why they think that's the answer.
Well, both areas have to be
I'll
equal.
do a hand raise in the chat. Oh, there's one raise, but I don't see who it is. Oh, John. Okay, what's your numerical answer to this question?
Well, the area of the square has to equal the area of the rectangle, right? So
Yes,
that means that the side would have to be 6 times 6.
that's right. Area equals 36, area equals 36, side length is 6. See, that's a great question. I pride myself on making up questions of this sort because, you know, telling you on a final to do the windmill proof, well, no, that would be an unfair question. That would be too long. But you have to understand you have to understand the plan of the windmill proof. Otherwise, how would you answer this question? You'd have no way. You'd have no way to.
Can you kind of identify the overlapping triangles? I'm just kind of curious here.
So the overlapping triangles would go, the trick is each overlapping triangle has the obtuse angle formed by the right angle and the shared angle.
Right.
So there's one of them.
Oh, okay.
And the other one uses this angle, this right triangle with this. So you just connect from here to here.
Okay.
Each one uses a side from the big square and a
Yep.
side from the little square.
Gotcha. So
That's a great question because those extra lines might have seemed pretty mysterious even up till now.
right. But you wouldn't necessarily have those auxiliary lines. We should understand they could be drawn in and therefore make the conclusion that 36 and 36 are the connections or the equal areas.
Yes, or just knowing that the general plan of 147 is to prove that this equals this, even without knowing that the triangles got used for them. Just knowing like the overall plan was to prove that the square and the rectangle had the same area.
Right.
So you don't need the triangles to do that if you know what the plan was.
Okay. So you would never
It
give
helps
us, would you on a test ever give us that and ask us to draw in the auxiliary lines and explain them, or you just going to make it a calculation question?
So this one would be a calculation question.
Okay.
I'd have to think, you know, I don't want to say for sure there's no way to check. Do you know, I mean, I could give this picture and say, you know, which two triangles are congruent, you know, draw the two lines that form the two important triangles. So it is possible that
Okay.
I ask to draw two lines, you know, it is possible, but
Okay.
usually I give these numerical sorts of questions.
Okay.
Now, before, I think I'm going to take a break, but before, I'm just going to do just 5 minutes now, and then I'll do the break, because I realize I haven't put anywhere into the course. What did the Greeks have against similar triangles? There are a lot of proofs that they do. Similar triangles don't come up until book 6. And once they do the similar triangles, they reprove the Pythagorean theorem with similar triangles. And they prove other theorems that were not proved with similar triangles. If you don't get to use similar triangles, they had a very bizarre theorem that they used instead. I don't want to tell you about what that theorem is. It's a theorem that's so confusing, but it didn't rely on a leap of faith that similar triangles require. So let's see what's the deal with similar triangles. What's so bad about similar triangles?
Does it have something to do with with measurement? Like they didn't trust measurement?
It, well, they didn't trust measurements in the, practically, where you're measuring stuff with a ruler,
Yeah.
but theoretically, you don't need to measure things. You could calculate what their measurements are, and they do trust calculations, but they still run into a problem. And look, let's see why. Here's I'm just going to go 6, 8, 6, 8, 12. It's not; these are not right triangles. Actually, I'm sorry. Let me make this one 6, 8, 12. And make this bigger one 9. Sorry, these are multiple. I want multiples of 3. So 6, 9, 12. 3 times 2. This is 3 times 2. This is 3 times 3. Yeah, I want to multiply each thing by 1.5. I don't like that so much either. I'm going to do it anyway. Now,
Bottom should be 18, right?
oh, 18. Now, when they talk about similar triangles,
The proportion should be the same.
yeah, and are they in this? Yeah, each one's 1.5 times the other. So what it means to have the proportion the same is that these numbers, 13 and 9, for instance, they are both divisible by 1.5. Right? 9 could be split into 6, 1, 2, 3, 4, 5, 6 pieces that are all 1.5.
Yeah.
Actually, 4.5 is also one, but I'll use different numbers for each of the sides to give the idea. So 9 and 13.5 have a common, what's called a common measure, which is the 9 could be split into 4.5, 4.5, and the 13.5 can be split into 3 of them. The 12 and 18, they have a common measure of 2. Right? I could split 12 into 6 2s, and I could split 18 into 9 2s.
Yes, or we can say 6.
And for the 6 and 9, I could change the 6 into 3 and 3, and the 9 into 3 3s.
Professor, and for 12, we can say 6, 6, and for 18, we can say 6, 6, 6 3 times on the same way.
You know what? That's right. For our purposes, it might make more sense. It might make more sense if I don't use the smallest possible one. And I'm actually gonna do that. So for this, I'm gonna make it 6, 6. And make this 3 6s. Thanks. This is going to help us understand it better. So with similar triangles, we can understand similar triangles better, that there's like some kind of common measure between the sides. And one of them is made up of some number of those, and the other one's made up of some different number. And that's what makes triangles similar. Now, line segments, any two line segments we figure we could do this with. Like, for instance, even if it's 5 and 7, I can say the common measure is equal to 1. And the 5 is cut into 5 ones. And the 7 is cut into 7 ones. And even if the things are not integers, 5.1 and 7.3, we could make really small things. I could use 0.1 as my common measure, and the 5.1 is made up out of 51 of them, and the 7.3 is made up out of 73 of them. Now, sometimes you have something with fractions, like 5 1/3 and 7 1/6. Anyone have a thought of what would be a good, if I want to find a common measure, a thing that kind of like can be spread out among both of those? You could type it into the chat. One third won't work because of the you can't get 7 and a 6, but 1/6 does work. So I could have all these 1/6 and all these 1/6. So when the Greeks thought about similar triangles, in their minds, they said, okay, there's some sort of a common measure of these line segments, and this bigger one's made up out of more of them than the other one. And that kind of, and that'll be true for the other sides also. This is just the idea. It depended on when two things have a common measure, when two segments have what's called a common measure. It's kind of like the least greatest common divisor. It's like the greatest common divisor. They are called commensurable. I'll write it down here. And it seems pretty obvious that any two line segments will be commensurable, because if you have to use a tiny measurement, you'll use a tiny measurement as the thing. And that was all fine until the Pythagoreans discovered that if you take a square and you take the diagonal of the square, which is the square root of 2, that there was no common measure between 1. So let's put them side by side, 1 and square root of 2. Now, it's not because it's a repeating decimal. Like, I could do 1 with 3 1/3, which is 3.33333 going on forever, by picking a unit of 1/3. And 3 1/3 would have 10 of them. So the problem was not repeating decimals, because you can't do 1/10 or 1/100th or 1/1000th, because you can't get 0.33333. 0.1 doesn't go into it. 0.01 doesn't go into it. 0.001 doesn't go into it. It's a repeating decimal, but 1/3 does. So with rational numbers repeating, that was okay. But with irrational numbers, they realized and they proved that there is no common measure for square root of 2 and 1. No matter how small you want to make it, 0.0000, 10 million zeros and a 1, it doesn't go evenly into square root of 2. They proved it, but it's very not going to show you proof of it. Can we just say that they proved it, as crazy as that might seem. I can't, I'm trying to remember what the proof is. Yeah, I can't remember it exactly. I'll look it up for you. I just wanted you to know that they proved that there's no common measure. So without common measure, they can't even if these are similar triangles. They can say they're similar, but they can't do their proportion because their proportion was, you might say, why can't they do their proportion? Square root of 2 over 5 equals x over 7. Seems like, of course you could do the proportion. You could actually calculate it. But they said, we're really not allowed to because our whole theory of proportions was based on the fact that if I split up the square root of 2 and the 5 into the pieces that have the common measure, and then I take the 7 and split it up into that many pieces and then multiply them. So they threw out, they said, we're not going to use similar triangles unless we have to, which is extremely sophisticated because you would think, okay, come on. Of course you could have similar triangles with a square root involved. The story is that the person who figured out, who proved that 1 and the square root of 2 were so-called incommensurable was named Hippias. And whether it's true, was he either it was a secret, you know, they weren't supposed to tell anyone when they found this out. And he told people, and he was potentially killed for revealing this secret, thrown off of a boat. Hippias, Pythagorean.
He was killed for giving out the top secret math. I think that's
what they say. Here, who discovered the square root of 2? Hippias discovered the square root of 2 is an irrational number. That is, he proved the square root of 2 cannot be expressed as a ratio. Here, let's just say Hippias, Pythagoras, killed. Some writers have Hippias making his discovery while on board a ship, as a result of which his Pythagorean shipmates toss him overboard. While one writer even has Pythagoras himself, to his eternal shame, sentencing Hippias to death by drowning for showing that the square root of 2 is an irrational number.
To be fair, it's important to remember Pythagoras was a cult, and that's probably why they were not wanting that secret out.
Yes, they were like a cult. They're vegetarians. They wouldn't eat beans or something. There's a lot of stuff going with Pythagoras. So discoveries were attributed to Pythagoras even after he died, that sort of thing. So I'm going to dig up, you might be interested, like how did they prove the square root of 2 is irrational? There's like a geometric explanation that like if it was irrational, if there was a common measure, it would mean that there was a bigger one. I don't know. It's a bit confusing. I'm going to look it up for you. But that's why. And similar triangle theory was dependent on numbers being commensurable. So so eventually somebody settled this, and they said you are allowed to use similar triangles. Someone named Anaxagoras came up with a theory called the Method of Exhaustion. I don't know how to spell it exactly. Came up with something called the Method of Exhaustion. And basically he showed that it's okay to use similar triangles, even with numbers that are irrational. And then in Euclid's Elements, they eventually in book 6 use them to reprove stuff, Pythagorean theorem and all. But they don't like them. They'd prefer not to use similar triangles if they can figure out a way to prove something without those similar triangles. I find that so surprising. Okay, that was very tiring. Let's take our 10-minute break now. And when we come back, we'll do part 2 of today. So I'll see everyone in 10 minutes.
Hi, Professor, are you here?
Yes.
About question 10, I think that I have a misunderstanding. I don't accept it one door with 2 separated pieces, but I understand with 2 doors, one after another. Like as my apartment, we have the first door, we open this one, and after we have another door. So
You're talking
Yeah.
about,
The homework,
the,
for the
the,
homework.
the Chinese word
Yeah.
problems?
Yes, yes. So we understand that
Yeah,
I
so I
open one door and after I open another door. So
Yeah, the doors, those are kind of really the 6 questions that we did in class are the ones I'm most interested in. But I did want to, to see what the things were. So I posted those. You get credit just for attempting to make a diagram for it, but I did want to show you what they look like. So I posted all those. Assignment 8. Let's take a look. So 7 was only delta math, right? That was the square root algorithms.
yeah.
So 8 is here, and 9. 9, there's no 9 was the construction, so there wasn't any work to do that. Yes, but yeah, number 10.
Mm.
I remember that one being difficult, and that's why it's on this other page. I had to really. There we go. Yeah, number 11, 12, 13. Yeah, it's so weird, right?
Yeah.
It's got the
Yes,
two
but number
doors
10,
and they like
yes.
open, but there's like a door stopper
Yeah.
to make this trapezoid. So you have that sort of.
Yeah, so I understand that we have 2 doors. I open one and after we have a difference between them and we open another door. This is.
Oh yeah, the 2 doors. They're like French windows. It's like the 2 doors are like
Yeah.
kind of touching each other. Yeah, then you open them.
Yeah.
Normally, there's not this like other thing that prevents the doors from opening all the way, but I guess they had it back then. Yeah, it was
Yeah.
actually hard to make these diagrams. I put more in because there's more questions, but I just, for our purposes, questions 1 through 14, actually just the 6 that I did in class are going to be sufficient. But they're interesting questions, like this one, number 9, with a log. It's like buried into the wall, but horizontally. That's kind of surprising. I'm only going to ask the 6 questions from class, but I put up. I really should give you the other questions. You might be interested. What were questions? 18 and all. Those weren't really go specifically. They had right triangles, but they were more like similar triangles questions.
Okay. Yeah.
Hey,
Thank you.
Professor,
Okay.
in the same vein, weren't you going to give us another set of the problems that are up for the test, but with different numbers so we could practice it a little bit more?
Yes, I would like to do that. Just take those 6 questions and just change the numbers.
Yep.
I have to make up good numbers, which is sometimes a little hard.
Right.
Usually you start with the answer, you start with your answer,
And work
your
back.
Pythagorean triple, and then you work backwards to what the numbers for the question would have to be, because often the questions are like you give in A and C minus A. So I'd have to like look at those questions a little better, especially the one where the 2 guys are walking. One guy's walking east.
Oh my God. Yeah.
One guy goes south.
Yep.
That seems like it would be a hard one to make up so that it works out nicely.
Yeah. No, absolutely. Because
So-
you got 2 triangles.
Yeah, so for now, just do those 6 with the numbers that they are. But I will try to make up other variations on those.
Yeah, because to be honest with you, I find like that unit was the hardest actually because of the, you got to set the problem up and then solve it,
Yes, so you'll definitely want to make flashcards for the 6.
Yeah.
If you can do each of those 6, you'll be in great shape. But I definitely want to give you at least, on next Monday is going to be a review day, and
Yep.
I will get that done at least by then.
Okay.
So worst case scenario, I'll give you that on Monday, but I'm gonna try to get it done before that,
Great.
or over the weekend, because I won't be planning these lessons take a long time to prepare. But for Monday, I'm not doing a lesson as much as a review, so I can get that.
Get in your mindset. Gotcha. No, that's great. Thank you. I appreciate that.
You're welcome.
And Professor, as far as the I don't know if you saw the second half of my question there. On the
Oh,
on the list for last Thursday, the non-construction things you identified, do we just have to be able to use them in calculations, or do we actually have to reproduce them through proof?
so if I asked you to prove something, like prove that the angle bisector construction works, you'd want to be aware of of SAS,
Right.
so you can use it as a reason.
I was
It's
thinking,
almost like I'm giving you a list of reasons that you're permitted to use in proofs, because some people might have other things memorized, some really more advanced theorems that they would use instead. But I want you only to use from this collection, and we only have a few of those.
got you. But I guess
I think they were like,
I'm sorry to cut you off. I just was thinking
Go
more
ahead.
like the exterior angle theorem. Would we ever have to prove that, or just apply it in a calculation?
that you just have to apply. That one, just for reference, to prove that would only to prove the exterior angle theorem.
Yep.
Would only take a few seconds. It would look like this. I'm just going to call this angle 1, angle 2, and
Yep.
angle 3, and I'll call this angle 4.
Yeah.
So you would say angle 1 plus angle 2 plus angle 4, measure of angle 4, is 180 degrees.
Yep.
And angle 3 plus angle 4 is also 180 degrees.
Yep.
So angle 1 plus angle 2 plus angle 3 is equal to angle 3 plus angle 4.
Right.
And then if you just subtract away, sorry, it's 1 plus 2 plus 4 is equal to 3 plus 4.
Yep.
And then if you subtract away the 4s from both. But no, you wouldn't be asked to prove that. But that's going to be a good one to be aware of for tomorrow's lesson, because it's going to get used twice.
Yeah.
So I'm kind of anticipating.
Yep.
But the set of theorems is very small. I mean, I think there's 5 theorems altogether, or 6, because those constructions are not theorems. 180 degrees in a triangle, exterior angle theorem, Bailey's theorem,
Right. The angle,
Isosceles triangle.
the
I
sum
think
of,
there's
also
like
the sum of
4.
angles in a triangle theorem, right?
That was the first one, yeah. And then there was I mean, SAS and SSS aren't really, we're counting them as like theorems, SAS and SSS. So it's like 6 altogether, and it's not going to get that much bigger than that either.
Okay.
I usually on the final don't ask you to do any sort of proof. It's almost all questions where there's some kind of numerical answer.
Gotcha. Oh, that's helpful. Thank you.
Okay, so welcome back from the break. We are now doing part 2 of today. Again, today, if you look back at the very beginning, you will see that I promised to teach 3 things. Pythagorean Theorem, 147. I think we have given that its worthy amount of time, because that's really important thing. And bizarrely, I would imagine even the math majors have never seen that specific proof before. I know, it's most people, even math teachers, never see that proof. Second part for today, construction of a regular pentagon. So we've seen that you could easily make equilateral triangle. That's not how that works. 1-1 was equilateral triangle. And later on, he shows, I forget what number it is. It's actually book 2 something. He pretty easily shows that you can make a square. It's actually not hard to make a square at all. you could just make some perpendicular lines. Imagine I had a line segment and I have the ability to make perpendicular lines. Then I could make like a circle like that. Make another perpendicular. So triangle and square are really easy. And so 3 sides, 5 sides, 6 sides ends up being easy also. Sorry, I should have said 5 sides. I meant 4 sides. 3, 4, 6. 8 sides is easy. 10 sides is easy. 9 sides is not easy. 7 sides is not easy. In fact, those two are impossible. Unless you cheat, use some other tool. So 7 sides and 9 sides are actually not even possible with those tools.
How did you get the 4th vertex on the square?
You can make, if you know how to make perpendicular lines, you could just make another perpendicular line, and where it intersects the other perpendicular line,
I
it
got you.
would create the 4th vertex. So 7 and 9 are actually impossible. But 5 sides is possible, but it's hard. Pentagon. It's possible, but difficult. And that's what I'm going to teach you now, how to make a pentagon, how to make a perfect pentagon with compass and straight edge. It has a lot of theory, so let's get into it. We might only get these 2 things done today. I'll have to see how we're doing. So the way they figure out how to make a pentagon is they start by saying, well, let's just draw one just by hand first, just and say it's a perfect pentagon, and just try to study it to see what some of the properties of it are. If you were to make a circle around it, all of these arcs would be the same size. They would all be 72-degree arcs. And if I draw 2 more lines, Grant, that's coming. That's right. If I draw 2 more lines, namely this one and this one, I create this red isosceles triangle. And the thing about that triangle that's real important is that see how this arc is half as big as this arc. I use a different color because I have red or something else. So this purple arc is half as big as the blue arc. And there is a rule in geometry.
Well, it's also true of the
There's
other
a rule
arc,
in geometry that
Professor.
if you have an arc, yes?
Isn't it? It's also true of the other arc, isn't it?
Yeah,
Okay.
there's a rule in geometry. I should tell you what number this is for Euclid's elements, but I'm just going to say it. First, I'll start by saying that the angle in the middle, called the central angle, will be the same measure in degrees as the arc is. Or
Yes,
it's also measured in degrees.
yes, that's true.
Now, imagine I take this 72-degree angle and I make it this way, so that one of the sides is like horizontal. And then I extend this to be a full diameter. And then I connect this to make like a obtuse triangle.
Yes, now we have 108 minus 72 is the arc in front of the new angle.
Oh, yes, yes. You could get this angle to be 108. And then what? What can you say about this angle here?
We know the sum of those two angles are equal to 72 by the exterior angle theorem.
That's right. Yeah, you could get, that's right. But this is only this one. But yes,
Wouldn't it be
this angle and
35,
Oh, it's got to be 36, right? Because they're.
they are both 36. Why, Scott?
I said they'd have to be isosceles because they're both radii.
That's right.
Yeah.
So if you don't even need the 108, you could use the exterior angle theorem. So what this shows is that if you have an arc, like a 72-degree arc, and you have a diameter as one of the, you draw a diameter, that this angle, it's called an inscribed angle, will be half the arc. And I'm just going to make a quick leap of faith and say that even if the inscribed angle is not formed by a diameter, if you just go to any random point on the circle, that angle will be half of what the arc was. I made a leap there. You could see it in this specific case, and I'm just telling you that it's always going to be true. I forget what that is. I'm going to look up in Euclid the rule that the inscribed angle, they actually would say it this way, just so you know, in Euclid's Elements, they would say that this angle, angle 1, is half of angle 2. There would be no mention of the arc at all. They would just say there's a central angle and there's an inscribed angle, and they intercept the same arc, and that the inscribed angle would be half of whatever the central angle was. But nowadays we talk about the arc. Back to here. So what this means is that this angle here is a 36-degree angle. It's half of 72. And this angle here is 72 degrees because it's half of 144. And this angle here is half of the other 144, which is also 72. That triangle is very important in the history of math. It's called the 36, 72, 72 triangle. And the reason it's important is if you somehow have the ability to create one, and then you put a circle around it somehow.
Then you can create a pentagon.
That's right. Then you could bisect the 72-degree angles, and those would form the 5 vertices.
That is so cool.
Well, we have a couple of issues now. Issue number 1, we know how to bisect angles, so that's good. But we don't know how to do 2 other things. We don't know how to make a 36, 72, 72 triangle, and we don't know how to put a circle around a triangle. But the hardest part is the 36, 72, 72 triangle. The Greeks did not talk about degrees. They wouldn't call it a 36, 72, 72 triangle. They called it an isosceles triangle whose base angles are double the vertex angle. They would have known, I'm sure they would have known that 36 was, 2/5 of 90, so that sort of thing, because they knew about 90-degree angles or right angles, but this is how they described it, an isosceles triangle with a base angle. So if we can learn more about that triangle, we can use it to make a pentagon. Okay, so the plan is make the 36, 72, 72 triangle. Oh, make the circumscribed circle and bisect the angles. And the hardest step is the 36, 72, 72 triangle. So here comes our facts. And actually I have this, I believe, in here. I actually made a little question. I should have told you. This one you could get really quickly, question 2. But then question 3 is the 36, 72, 72 triangle. So we don't know anything about it. So let's just say, since every 36, 72, 72 triangle is going to be like similar to all the other ones, what if the two sides, the two legs, were both 1? And the question is, how big is the third side? Anyone know how you could do this with trigonometry? If you had trig wasn't invented for hundreds of years later. Greek also. Ptolemy had trig chart, 100 AD, but this is 300 BC. Anyone know, what would you type into your calculator? What single, like, it's sort of complicated, but what if you could just type one thing into a calculator, an expression, what expression would give you the side of the 36, 72, 72 triangle?
Is it okay to
Cosine?
add a midpoint bisector first?
Yeah,
AB?
that will definitely help, because in an isosceles triangle, the median is also the perpendicular bisector. So we'll call this x over 2 and x over 2 now. I see. Yeah, you won't need the law of cosines because we're going to use right triangles. But you could use the law of cosines. You're right about that. 1, 1, 72, 72, 36. You could use law of cosines, but I want to not introduce law of cosines because the math teachers might not be familiar with it. But they are familiar with cosines.
Yeah.
Cosine, here this is 72. Cosine of 72 is equal to adjacent over hypotenuse. Weird. Yeah, so x is equal to 2 cosine 72, which is about 0.6018. So let's just keep that number tucked away. If I also instead said, well, what if I instead chose to make the base one and put the x's here? then you would say cosine 72 is equal to 1/2 over x, which would make x equals 1/2 divided by cosine 72, which would end up becoming 1.618. Hold on. No, not 6018. Wait. 618. This is 618. Anyone can verify that 2 cosine 72? I'll do it on my 2 times cosine.
Does anybody recognize that number? 1.618, et cetera?
Yep,
Golden.
that's coming.
Golden ratio.
And that's part of today's lesson point. So 0.618 is the answer for this question. And if you add 1 to that, you get the answer for this question. And so I want to say now, what's so special about 1.618?
The golden
I've
ratio.
never heard that number before.
I'm so excited. Golden ratio.
Golden ratio. So let me explain a bit what we mean by the golden ratio.
It like shows up in everything.
Yes. Now the golden ratio officially is defined as you have a line segment and you want to put a point somewhere on it, somewhere around the 2/3 area. And the golden ratio is, it's the golden ratio. This point is at the perfect spot if AB over BC, which is the big piece over the small piece, is equal to AC over AB. If that's true, AB over AC is something bigger than 1 because AB is bigger than BC. AC over AB is also bigger than 1 because AC is the whole line segment and AB. But usually it's not true that AB over BC equals AC over AB. That's generally not true. But if it is true, then we say that B is the golden section, the spot that makes that true. And it turns out that it will be true if AB over BC is about 1.618. So just to show you, imagine BC was 1 and AB was 1.618. So 1.618 over 1 is equal to 1.618. But 2.618, the entire line segment, divided by 1.618 would also equal 1.618. 2.618 divided by 1.618 is also, yes, that's right. So they define this with the Greek letter phi.
Hi.
And it seems like a pretty arbitrary thing. Why would I care about that point so much? Like, why is that, important in any way? Well, oh, by the way, this 1.618 is an approximation for an irrational number. If I want to actually calculate out what phi is, exact value.
Yes.
Yes? Yeah, you want to go ahead? Here, I'm calling it x right now. So phi is equal to x over 1 is equal to, if it's really in the right spot, what goes in this other fraction?
X plus
It's
1
not in the
over
right.
X plus 1 over X.
That's right. The small piece, sorry, the big piece over the small piece needs to equal the entire thing over the big piece. And then you cross multiply and get x squared equals x plus 1, which we then move everything over to one side, and it's not going to factor. So we use the quadratic formula, negative b plus square root of b squared minus 4ac. I did plus 4 because of the negative there, over 2a. And we get 1 plus square root of 5 over 2. I'm going to write over here x equals negative b plus, I know it's plus or minus, but the minus is going to be a negative number, so there's no way that x has to be bigger than 1, so I'm only going to do plus. The square root of b squared, which is minus 1 squared, minus 4 times a times c, which is minus 1. That's why this becomes a plus, because there was a minus here and here, over 2. So that's called the golden ratio. And in Euclid's Elements, they actually teach you how to construct it. So Grant mentions that there's something called the golden rectangle. A golden rectangle has the ratio, the base to the height is the ratio of the base to the height is golden ratio, so it's called the golden rectangle. And it comes up in nature sometimes. It comes up in nature for kind of strange reasons, like evolution-wise, like an animal that grows in a certain way, like the most efficient way, will have this golden ratio. So it like takes the least amount of energy to grow in this way. So the golden ratio appears in the animal kingdom.
I mentioned that
And because what's that?
I mentioned you can actually see it when you look at the center of a sunflower. The seed pattern happens to be the golden ratio because it is the most.
Yes.
Yep.
Yes. So there's something about the golden ratio where when like plants grow, the ones that survive more than any of them are the ones where the angle between the leaves is related to the golden ratio. And so the golden ratio pops up in nature. Now, if it pops up in nature, it's going to pop up in art also, because what do we draw? You know, we draw things we see in nature. However, you should know that sometimes people have taken this argument too far, and there's not evidence for it. Golden ratio in art. So you will find many pictures like this where they will show you that the golden ratio is in various famous artworks. But you should know that that's been debunked. Yes, in actual nature, the golden ratio appears. So in actual artwork, sometimes the golden ratio appears because they're drawing something that was from nature. But there's no evidence that, for instance, Leonardo da Vinci made a golden rectangle and put the Mona Lisa's head, into it as his way of making it. So some people take this too far. It's been debunked.
Hey, Professor, is there any connection between it and the, was it Fibonacci sequence?
There is actually,
Big
yes, that
time.
one,
Big time.
that one, there definitely is.
If you look up
Um,
the orchard problem, and you'll see the relation between golden ratio and Fibonacci really well.
I might on the European day say some stuff about Fibonacci. I mean, we could have an entire day just about properties of golden ratio. But historically speaking, for now, we'll say the golden rectangle is a thing, and the golden ratio may not be in art, but it's going to be somewhere else. Because not only is there a golden rectangle, but if you were to make a triangle, isosceles triangle, and make the sides 5, 5, and 1, that would be a golden triangle. Now check this out. Big thing about to happen. If I take my 36, I need my, hold on, let me find it. Where did my big 36, 72, 72 triangle go? There it is. If I take my 36, 72, 72 triangle, okay, let me make a copy of and I call, which way should I do it? I'm going to call this X. And call these 1. Actually, I think this is better if I call this 1. These X. Now, without trigonometry, it's really hard to answer this question. But it's possible. Step 1, make an angle bisector through this angle. Now, when you do that, you will notice that this triangle here has a 36, 72, but there's a 72 here also. And this angle is 108 degrees. So what I have is 2 isosceles triangles now. Another 36, 72, 72, and a 36, 36, 108. I made this X, this 1. That's X. It does not seem possible to figure out what X is without trigonometry. But we are going to be able to. Because this little guy, DBA, is a isosceles triangle. So the length of the angle bisector is 1 also, because that's an isosceles triangle. Now that I have I called it D prime, but now that I have AD as 1, CD is also 1 because this is an isosceles triangle also. 36, 36. So I'll make this other one green. Can someone tell me about DB? Can you say anything relevant about line segment?
Other than it's
DB? You can type it in.
other than it's x minus 1.
Yeah, that's it. We can call it x minus 1. And now we're ready. That was the key. Because the little triangle, the small 36, 36, 72 triangle is similar to the original triangle. I'm going to draw them side by side. It might be easier to see what's going on. And now you can set up a proportion. X over 1 equals 1 over x minus 1, which turns into x squared minus x equals 1, which turns to x squared minus x minus 1 equals 0, which is the exact same quadratic equation from before. So the golden ratio is actually, or a golden triangle, the big side to the little side has a ratio of 5.
Come again? Could you say that again, please?
The rate, so in any 36, 72, 72 triangle, the ratio of the big side, which is, the leg,
Yep.
divided by the base will equal 5. In other words, 1.62, or exactly 1 plus square root of 5 over 2. So the golden ratio, its importance is that it helps us make a 36, 72, 72 triangle. Now, I just want to mention that if I instead put the 1s here and the x there, now it would be equal to 1 over 5, which actually is equal to just 0.618. I'm tempted to do this again. X over 1 from the big triangle is equal to 1 minus x over x in the small triangle. The only difference between this and the last one is there's a plus there instead of a minus. And you end up with -1 plus the square root of 5 over 2. So this is going to lead us to our method of creating this triangle. And once I have the triangle, I just have to somehow stick a circle around it, and then I could bisect the two angles, and out will come my my thing that I want to make. Hold on, let me just take a quick look over here. Let's see, hold on a sec. Okay, so again, the general idea is going to be somehow make a golden ratio. I'll tell you about that in a second. Use it to make a 36, 72, 72 triangle. Make a circle around the 36, 72, 72 triangle. Make the two angle bisectors. And in that picture is the Pentagon. That's the general idea. Of course, I'm going to go through this nice and slow, but at least I want you to see what the, what the plan is. I want to make sure there's two ways I can do it, and I want to make sure I did it. Okay, yeah, I think this way's better. Okay, so here it comes now. How to, whoops. How to construct -1 plus the square root of 5 over 2. Because if I can make a line segment that's that length, if I can accomplish it, then I could just very easily make a circle with radius 1 around this center, and then another circle with radius 1, and I'll be able to have the 1, 1 -1 plus square root of 5 over 2. I want everyone to take another 5-minute break, because I want to make sure I have this set up nicely so that you can play along with it. So let's do one more 5-minute break now.
Okay.
Okay, Professor.
Okay, everybody. I'm back. I had to make sure because there's actually two ways to do this, and I wanted to. One way to do this is to go like this. One. To make your golden rectangle this way, and then make your circle, and then your two angle bisectors. Or I can make it smaller and put the ones here. Still makes pentagon, but I did want to make sure that the ones that I have in my videos and stuff matches with it. It turns out it's this one we're going to do. So what we need is, see, we have a line segment of length 1. That's going to be the base of my 36, 72, 72 triangle. But now I need a line segment whose length is 1 plus square root of 5 over 2, which seems really hard to do. But it's actually not as bad as you would think. Let me come over here. I actually put a link in for you. Let me come over here and go. And I'll take you through the steps. This one, all the steps are done. It just lets you like play through them. But I'm going to talk about them. It's loading a little slow. There. Okay, so the very first step the observation, we need a square root of 5. Square root of 5 is critical, right? We want 1 plus square root of 5 over 2, which is about 1.62. But the hardest part about that is where's this square root of 5 going to come from? And the answer is?
Professor, we can't see what you're writing if you're trying to show it.
And the answer is the square root of 5 is the hypotenuse. The square root of 5 is the hypotenuse of a right triangle that has sides 1 and 2. So if I just make a segment of length 1 and make a segment of length 2 and make them at right angles to each other, and I just connect their endpoints, I've got a nice square root of 5. So that's really getting closer to 1 plus square root of 5 over 2. The next thing I can do after I have that, here you can see okay, the next thing that they did was they made a circle with radius 1. So now if I extend this line, which I'll use a different color for, that'll be 1 also. I'll just take some letters here. That's O, that's A, that's B. This is C. So let's make a note. BC is 1 plus square root of 5. Literally, I just took the square root of 5 and extended it by 1 unit. And we learned how to make midpoints. So if we were to go through that construction, I get a point somewhere over here. I'll call this D. And say that BD is 1 plus square root of 5 over 2. D is the midpoint of BC. Here it is on this thing. It's called E in this one. So now I have a line segment, CE, that is 1 plus square root of 5 over 2.
Which is golden ratio.
That's right. And then they use that to create a golden triangle. So let me talk about how you would have done this.
What?
Now you open up your compass to that length. You know, I really should do this totally from scratch. This will be a lot easier for you to understand if I do that. So let me come over here. I'm opening up a new window. Hold on. It's coming a little slowly. I love GeoGebra. Really an amazing program. Tools, I usually turn off all my, I'll say new points only, and I don't need to see all that. Okay, so first, that's my line segment. That's going to be my 1 unit. Now I want to make the square root of 5. So I'm going to say make a perpendicular line. I want to make a 1, 2 square root of 5 triangle. Whoops, why did that not? Perpendicular line, select point and the line. Weird. Try this again. Perpendicular line. That's better. Now, to get a line segment of length 2, it's not too hard. I could just go like this. Because these are radii of the same circle, AC will be length 1. And then I can make another circle. And AD 2. Then I connect these 2 points. There's my square root of 5. To make things a little easier, I'm going to hide those 2 circles because those are a little, and this point actually served its purpose. Now I'm going to make a circle of radius 1. Not there. I'm going to make a circle of radius 1 here. And now I'm going to make a ray to extend dB. dB was square root of 5. B, here's this intersection point. BE is 1, which makes DE from D to B is square root of 5. Tack on B to E is 1. So that whole line segment is 1 plus square root of 5 over 2. This circle served its purpose. I'm taping this video and this whole thing also. I don't need this whole ray anymore. In fact, I'm going to hide this also. And here is my 1 plus square root of 5 line segment. But I don't want 1 plus square root of 5. I want 1 plus square root of 5 over 2. And that's where the midpoint comes in. I think I just click on these 2 points. So from D to F is 1 plus square root of 5 over 2. That's where I was in the construction. Just to not, we don't need to see all this stuff anymore. So I'm going to hide so much. All this work was to get me segment DF. df is 1 plus square root of 5 over 2. But how do I put these all together into one triangle? Well, on GeoGebra, if I click on this, it tells me this line segment is called K. So all I have to do is come over here and say circle with center and radius, and just go like that and type in K, and it makes a circle. That circle has A as its center and has df, which is 1 plus square root of 5 over 2, as its radius. And then I do that again over here. And now if I come here to intersect, this BG is going to be 1 plus square root of 5 over 2 because it's part of a circle that has radius 1 plus square root of 5 over 2. And AG will also have length 1 plus square root of 5 over 2 because it came from circle A, which had radius 1 plus square root of 5 over 2.
Is AB supposed to be a radius? Because I'm so confused.
No,
right
no, AB was length 1. AB was length 1.
But
We started with AB.
BC and AC are radius.
BG, you mean?
Yeah, is G.
Yeah. So A and B were the endpoints of the original line segment that had length 1.
right.
Then I went through a whole series of steps that got me this random other line segment, which is it says DF.
Right.
That was 1 plus square root of 5 over 2.
Got that.
My goal was to make a triangle that had 1 as its base, namely AB, but its other two sides had to be 1 plus square root of 5 over 2.
Right.
So I made those two big circles. Each of those had radius 1 plus square root of 5 over 2.
Oh, okay.
And where they came together, AG, A to any point on that circle, the left-hand one, would be 1 plus square root of 5 over 2.
I got that.
And B to any point on the right-hand circle will be 1 plus square root of 5 over 2. So if I go to the intersection of both circles, I have a triangle that has everything I need. 1 square root of 5 over 2, square root of 5 over 2. And I'm actually going to hide. I don't need this anymore. Or this. Or this. I don't even know what this H point is doing there. And in case you're wondering, did this work? (72 degrees). Wrong way. (72 degrees). (36 degrees). So it did work. Now we need some angle bisectors. Actually, if you don't mind, I'm going to do the angle bisectors last. We need a circle around this triangle now. And
How you can
I think I'm
find
just going to,
the origin?
the center of this triangle. So I'm just going to tell you, without proving it or anything, I'm just going to tell you that if you make two perpendicular bisectors, any of the two sides, doesn't matter which two, if you do that, and you find the intersection of the perpendicular bisectors, and you make a circle that goes from that point, oops, and you make a circle that has that as the center and goes, whoops, not that one. I want to go circle with center through points. If I make that my center, it's called the orthocenter, I think, and I go through any of the three vertices, I promise you, it will go through all of the vertices.
Wait, so you have to do an angle bisector with a perpendicular bisector?
No, just I did two perpendicular bisectors.
Okay.
This is also, all we need to know is that we need a circle, but I figured I'll just tell you that this won't be anything you tested on or on the final, how to get the circle around, because I didn't tell you about that. But now that I have, now I'm going to hide those two lines, the perpendicular bisectors that helped me get the center of the orthocenter, it's called, of the triangle, that helps me get the circle. We finished this thing out with the angle bisectors.
Yes.
Angle bisector number 1, angle bisector number 2. And where those angle bisectors hit the circle, those will be the other 2 points of the pentagon.
So you need perpendicular bisectors, then angle bisectors.
The perpendicular bisectors get me the center of the circle I need to go around that triangle.
Okay.
But the perpendicular the angle bisectors get me the other 2 points of the pentagon. So that's pretty nuts. Let me bring back this. And I have here, now that I've done it nice and slow, we can actually just easily go through this and kind of think about, okay, what happened? I needed a length of 2, so I can get a square root of 5 plus 1. That gets me square root of 5 plus 1 over 2. I use that to get the golden triangle. I put a circle around that triangle with perpendicular bisectors, and then I have angle bisectors that got me the 2 points I needed for my pentagon.
Yeah.
Okay. Well, that is pretty crazy,
Amazing.
and that's all we'll have time for.
So
I'll stick around for 15 minutes now. So I didn't do the third thing. This was plenty for one day.
so the
Question?
length of CE is the same as BF?
Where's C on this picture?
Yeah.
Oh, on the one I had from before. Where's
No, this picture, this picture.
Oh, CE, yes. CE is the same as BF, is the same as FA.
Okay.
That's right.
I see it. Thank you.
You know, it would be a good question, like, what's the deal with point E? You know, it's the midpoint of CD. You know, and why do we want it? Because CD was 1 plus square root of 5, and I wanted 1 plus square root of 5 over 2. Why did you want 1 plus square root of 5 over 2? Because earlier I showed that in the 36, 72, 72 triangle, if the base was 1, the legs had to be 1 plus square root of 5 over 2. You know, you kind of work your way backwards. Like, why did you know, what did each of these things accomplish? The golden ratio was invented for the purpose of constructing a regular pentagon with a compass and a straight edge. Then they found other uses of it later. Now, because we didn't do the third thing, I am going to remove from the homework assignment any questions about Archimedes and pi. Where is that? Assignment 10. So I'll make a note here. Oh, I see. It doesn't leave very much. It only leaves 3 questions, but I think I'll put a thing for you to do the construction also. So I'm going to make these aren't due for 2 days, but I'm going to say these will be for Tuesday's lesson.
So we're gonna have to do that construction.
Well, for that construction, I have a I have one of these GeoGebra things where you get to do it.
Okay.
So let me just find that, and I'm going to assign it to the class. But I'm also going to give you a video that shows me doing that construction, and the
Okay.
whole video is I think 2 minutes long.
Okay.
So let me. You can stick with me if you want to make see that I provide this to you properly. So let's see. Construct regular pentagon. Let me dig this. Hold on. I'm going to assign this. Yes. Let's see. Book 4, proposition 10. Wow.
We can't see.
Yeah, I'm about to assign it. So let me do this. Share. Oh, that's interesting. Embed. I don't want to embed. I want to share as a okay. Very strange. I'm gonna have to work on that. Why would that? Maybe I click here. Bizarre. It's only letting me embed. It's not letting me share it as. Okay, I'll work on that. For today's lesson, the main thing that you want to know is the Pythagorean theorem. The Pythagorean theorem proof. Those triangles. I might say on the final, here are the two triangles. Why are they congruent? You'd say SAS. Here's the square and the rectangle. What's the deal with them? They're the same area. And the golden ratio and why it's important, how the golden ratio factored into the regular pentagon construction. I think I'm going to at least put up there the thing that you see on your screen now, because I think this on its own is a great thing for you to just click through. You can kind of click through it, and at any moment you could just ask yourself, what do I know the length of every line segment in this picture? Not those, but, and then you can kind of go backwards also if you get stuck. So that is already posted in the, that thing is already posted, I think, or if it's not, let me go ahead and put that over here. Is that what this is? I'll just put another one. Yeah, looks like it's the same thing. Okay, so I'm going to be, because the homework currently is just 2 questions, because I was planning to do a more involved thing as part 3, which is what most of the homework was going to be based on. I might add a little something to the homework, but not very much. I just have to get it working. Something about, more questions about the proof of the Pythagorean theorem and the regular pentagon construction. But currently, the homework is just 2 questions, which the first one only takes you 10 seconds. And the second one, takes a little bit longer, but not much. The homework was going to be extensive, but I never got to that third thing because I don't want to rush and leave people behind. I'm not in such a rush through these topics. So stay tuned. I'll post something up soon for assignment 10.
So if you do post something additional, it'll be more like talking about the lengths, how like identifying the lengths of different segments as you construct it.
That would be a very good question. Like for instance, if I gave you this picture.
Yeah.
All done. and I just asked some questions about it.
Okay.
You know, it's an excellent question. For instance, what's the length of IF? I like that one.
Okay.
AB, it's given that AB is length 1.
Right. AB length 1.
So what would when this whole construction is done, what's the length of IF?
Wouldn't
I
it
don't-
also be 1? Because it's a regular pentagon.
It's also
or
1
equal?
because the goal of the construction was to make a regular pentagon. So if AB is 1, IF needs to be 1 also.
Great.
That's an
And-
example of a question I like.
And maybe would you ask what type of line is like going through vertex? Like, in other words, you would ask us to identify the perpendicular bisector versus the angle bisector, maybe? Or is that?
Yes, I could say, well, what's the deal with AK?
Okay.
And you would say it's the angle bisector of angle BAF.
Because that's kind
Or I
of,
might say, what's the deal with segment
IG.
G? That's funny. It's funny that IG came up. IG. I'm surprised that IG is intersecting with BI. Because IG,
It's an angle
it seems to
bisector,
hit.
right? And a,
Yeah, but IG was the perpendicular bisector. So what
Yeah.
I'm surprised about, I didn't actually need to make those angle bisectors. I needed to, because it's not at all obvious that the perpendicular bisectors should also go through. But when you think about it, the perpendicular bisector of KB is bisecting that side. So I is going to go through. So I didn't actually need the angle bisectors, but I wanted them.
yeah.
Because those perpendicular bisectors were for me to get the circle I needed.
Right.
So I didn't even realize in my whole life that those two lines, I usually delete them. I usually hide them before I do the next step.
But you'd have to recognize it only happens to the upper 2 vertices because, right? Because it doesn't apply to the other perpendicular bisectors.
Oh yeah, that's right. That's right. I'd have to do perpendicular bisector of sides BD and AI. Otherwise, it wouldn't work. So this was like bad luck for me.
Yeah.
I should have chosen I chose just the 2 sides that make it look like you don't need angle bisectors.
Yeah.
That was a poor choice.
Professor, will you be posting
Yes.
the notes, the whiteboard notes?
Yes.
First class?
In fact, let me get those ready to go. Email current file. Okay, so those will be posted pretty soon. Oh, and let me stop the video because once the video stops, I'm able to, it takes about an hour.